Okay, so this is the practice test that I gave you today. So I'm just going to go through these right quickly. You already know the answers to these. Number 1 should have been D, and 2 should have been B. They've given me the prediction equation. So this y hat equals 64.93 plus 0.63x. So immediately I'm going to go underneath this and put in what they are, where it says y represents the height in centimeters, and x is the age in months. So if I know the age, I can predict the height. So they told us he's 22.5 months old. So all we're going to do is plug in 22.5 for x. Just put it back where it came from. And when you plug that in, sorry, he's talking to me. When you plug this in, I ended up with the predicted height being equal to 70. No. I can't tell what I'm doing here. Yeah, 79.105. That's right. That's D. That's what I got. All right, and so that's what I ended up with, which D is the best answer. Then it tells us that Loretta is 20 months old and she's 80 centimeters tall. What is her residual? Well, Loretta is 20 months old, so that's her age in months, and she's 80 centimeters tall. That's her Y. This is the observed value. So now they're asking us for her residual, so we have to go figure out what her predicted height would be. So when I go plug in 20 to this formula, I ended up with 77.53 for her predicted. And so now residual is simply y minus y hat, observed minus predicted. So 80 minus 77.53, and I ended up with 2.47, which is B for her residual. Number 3, you have data for families on the parent's income, and so they go ahead and tell us that your initial examination of your data indicates that children from wealthier families, so wealthier means as they have more and more money, so as their money increases, they also tend to go to school for longer. So this would assume 0, 1, 2, 3, all up to 12 to college, etc. So we would think that as money increases, so does their years of schooling. So we would think that the explanatory variable would be the parent's income, but we would think there would be a positive association. So we would think that their income may explain how long they go to school. And so we would think explanatory is parent's income and a positive association. So B for number 3. Number 4, community college analysis. The correlation is negative 1.08, and it should simply be E. Correlation cannot be below -1 or above +1. Correlation between corn prices and soybean prices is R equals to 0.7. So this means that, so first of all, this is positive correlation, which means that they're both increasing. So as corn increases, soybean increases. So when corn prices are above average, soybean prices also tend to be above average. Letter B, there's almost no relation. That's not true because 0.7 is moderately strong. When corn prices are above average, soy prices tend to be below. That would indicate a negative correlation. When soy prices go up by $1, the corn prices go up by 70 cents. That would be trying to talk about slope, and that is not how you interpret R. The economist is confused because correlation makes no sense in this situation. That's not true. A is our best answer. This is the one I tried to tell you right quickly, that this is always going to be true. If you take all the mean of all your x coordinates of a scatter plot and the mean of all your y coordinates of the scatter plot, then that point will always fall on the prediction equation, or the least squares regression line. Correlation and regression require that there are clearly identified explanatory and response variables. Scatter plots require that both variables be quantitative. This is true. And this is also true. You do have to have quantitative variables to do scatter plots. This is kind of iffy or misleading. Correlation and regression require that there are clearly identified explanatory and response variables. Correlation does not. Remember, if we switch the x and y, you end up with the same correlation. If you did the least squares regression line of L1, L2 or L2, L1, the correlation, the R value stayed the same. So that is what makes that not true. Regression, yes, you need to know which one goes on the x-axis, which one goes on the y. Correlation, you do not. You can find out the strength of their relationship without knowing which one is x and y. There's an approximate linear relationship between the height of females and their age from 5 to 18 years described by the predicted height. So this is our equation. Predicted height is equal to 50.3 plus 6.01 times their age. And this is in centimeters, and this is in years. And they've already told us it's only effective from 5 to 18 years of age. So, which of the following is not correct? The estimated slope is 6.01. That is the correct slope, which implies that female children between the ages of 5 and 18 increase in height by about 6 centimeters for each year they grow older. That is the correct interpretation. So if this is 6.01, it's change in y, which is height, over age, which is years. So every time they increase in height and age 1 year, their height increases by 6.01. So that's true. The estimated height of a female who is 10 years old is about 110 centimeters. And so we're going to plug in 10 years of age, 6.01 times 10 plus 50.3, and see what the resulting age is, and I think that does turn out to be about 110. The estimated intercept is 50.3. That is true for the intercept. We can conclude from this that the typical height of female children at birth is 50.3. That is not true. That is the y-intercept, and if you had to interpret it, you would say the line says that at age 0 the height is 50.3, but we cannot conclude that that's the typical height. We know that that doesn't apply here because they told us this is only effective for ages 5 to 18, so no, you cannot conclude that that is the case. The average height of female children when they're 5 is about 50% of the height of when they're 18. So if you plug in 5 into the formula and then plug in 18 into the formula, I think I just did that on the calculator, but if you plug in 5 and get the estimated height and then plug in 18 and get the estimated height, this number is about half of that number. Niece is about 8 years old and is about 115 centimeters tall. She's taller than average for girls her age. And so if you plug in 8 into the formula, you will end up with something less than 115. So she is above average for children that are typically 8 years old. Number 8, you're interested in predicting the cost of heating houses on the basis of how many rooms the house has. A scatter plot of 25 houses reveals a strong linear relationship between those variables, so you calculate a least squares regression line. Least squares refers to minimizing the sum of the squares of the 25 houses' heating cost. So that would be the sum of the squares of the y-coordinates. Nope. Minimizing the sum of the squares of the number of rooms in each house. Nope, that'd be like minimizing the sum of the squares of 8 of the x squared variables. Minimizing the sum of the products of each house. Nope. Minimizing the sum of the squares of the difference between each house's heating cost and the number of rooms. Not the difference between x and y. It is minimizing the sum of the squares of the residuals, the difference in the y and the y hats. So E is your correct answer for E. Number 8 again, we don't need to do it again. Number 9, study a least squares regression line was fit to the data, and here is the residual plot. What does the residual plot tell you about the linear model? And this is your best answer. It definitely is not random or scattered, so therefore it tells you that it's not a good linear model. To be linear, it needs to be random. All right, and then number 10, which of the following is statement true? All right, so Da Vinci, the Renan Pater, speculated that an ideal human would have an arm span that is equal to his height. So basically, arm span would equal height. That's the equation that he predicted, or he thought. The following computer regression or printout shows the results of a least squares regression line, both in inches, for a sample of 18 high school students. So now we've got to actually come up with the equation that we got from a sample of 18 students. So this is saying constant is 11.5474, so that's my y-intercept. The coefficient of height is 0.84024, and that goes in front of height, and it's positive, so that means I must be predicting y. And so height is my x, then my arm span must be my y, because this has got to be the number in front of x, so this is x, and so it tells us then it is the height, the least squares regression of arm span on height. So there's height, so y must be my arm span. So that's the difference. This was his little equation. That's what he thought, arm span just equaled height. This is what we found out to be, that arm span equals this formula based on our 18 samples. So, which of the following statements is false? The least squares regression model would make a prediction that is 1.64 inches higher than Da Vinci projected for a 62-inch tall student. So for a 62-inch tall student, I'm going to plug in 62, and I don't know that I wrote this down. Oh yeah, I did. So when I plugged in 62 into this equation, I ended up with, that's not right, let's do it again. So 11.5474 plus 0.84024 times 62. Oh, this said go to. I messed up. Alright, so let's try that again. Okay, what is wrong with my calculator? Okay, so I went back and plugged in. For some reason my calculator was goofed up. I plugged in 62 into the formula, and when I plugged in 62, this prediction equation says we would predict the arm span to be 63.64 inches if they had a height of 62 inches. But if we plug in 62 for height here, the arm span is exactly 62. So the first one says that the linear regression model would make a prediction that's 1.64 inches higher than his, and so that's about right. 1.64, 63.64 minus 62 is about 1.64, so we agree with that one. If one of the students in the sample had a height of 70.5 inches and an arm span of 68, so 70.5 inches in height and an arm span of 68, then the residual for this student would be negative 2.78. So what we're going to do now is plug in 70.5. This would be an observed value into the prediction equation. And so 70.78 is what I ended up with for the predicted value. So then if you just subtract 70.78. No. We do observed, observed first. So 68 minus 70.78, the predicted value. It is negative 2.78, so that is true as well. The least squares regression line has a steeper slope than the equation for Da Vinci's relationship. Our slope here is 0.84. His slope here is 1. And that is not true. 1 would be a steeper slope than 0.84. So number 10 is C. This is true for every 1 inch increase in height. The regression model predicts about a 0.84 inch increase. That's just the interpretation of slope. And for a student that's 66 inches tall, our model would predict an arm span of about 67 inches. So if you plugged in 66, you would get something close to 67. So they're all right except 10, which is C.